Welcome to The White Space, a podcast where we talk about data centers in a simple and practical way.
Welcome back to The Deep Dive. I'm really excited you've joined us for this, our fifth deep dive from the White Space Piso Blanco podcast. If you're new here, the White Space is, well, it's your shortcut to getting truly well-informed. And today, we're diving deep into something absolutely vital for modern enterprise infrastructure, cooling strategies inside data centers. But before we jump in, a massive thank you to our fantastic sponsors, Series Tech and Noxtel. Honestly, their support makes these deep dives happen. You can find all the important links right there in the episode description. Okay, so the white space. When we talk about that in a data center context, we mean the actual physical floor area. It's where all the critical IT gear sits. You know, your servers, storage, networking equipment. It's where all of the processing magic happens. But it's also where a ton of heat gets generated.
Which brings us right to the core challenge for today, the cooling imperative.
Oh, it's more critical now than it's ever been, really. Just think about it. Every single server, every switch, it's like a tiny heater. And we're constantly pushing to cram more power. We're talking high-end CPUs, powerful GPUs into smaller and smaller boxes, especially for things like AI, machine learning, high-performance computing. The heat loads, the rack densities, they're just going through the roof. If you don't have really solid cooling, that hardware doesn't just slow down, it can fail, like meltdown fail, leading to outages and, crucially, data loss that businesses just can't afford. It's about stopping a very, very expensive disaster before it starts.
Right. So before we look ahead, let's talk about the traditional method, the reigning champ for a long time, air cooling. We all know air conditioning. But how does it work scaled up in that enterprise data center white space?
Yeah, the most common setup uses a big central air conditioning system. Often, it's tied into what's called a chilled water plant. This system pumps out cold air, sends it through ducts, usually under the floor, into what they call cold aisles.
Cold aisles, okay.
Exactly. So this cold air blows across the IT gear in the racks, picking up all that heat. Then, the now warm air gets funneled out through hot aisles and piped back to the AC unit. It gets cooled down again, and the whole cycle repeats. It's basically a continuous loop.
Okay. Simple enough, and it's been the standard for ages. What made air cooling the go-to choice for so long in data centers?
Well, a big part is just familiarity. Air conditioning tech has been around for over a century. It's refined. IT engineers, they understand it. They're comfortable with it. It's proven. Plus, you've got a really wide supplier base, lots of vendors, easier to get parts, quicker repairs usually. And, generally speaking, air doesn't damage electronics, which is a plus. It also offers a good amount of agility. Staff can move things around, make changes fairly easily.
Sounds reliable. But I guess it must have limitations, especially with IT demands just, exploding, like you said. Where does air cooling start to struggle?
You nailed it. The core issue is efficiency. Air, just as a substance, is much, much less effective at moving heat compared to liquids. I mean, water, for example, can carry something like 3,500 times more heat than the same volume of air. Liquids overall, maybe 20 times more efficient easily. So it takes a lot more energy to cool down warm air than it does to cool down warm liquid.
And less efficiency, that means higher running costs, right?
Directly, higher energy bills to get the same amount of cooling done. And from a sustainability angle, that high electricity use usually means a bigger carbon footprint. Unless you're lucky enough to run on 100% renewables, which is, let's be honest, rare. Also, many large air cooling systems use evaporative cooling, think cooling towers, which can use enormous amounts of water. That's a huge problem in places where water is scarce.
So even if you just keep pouring more power into it, does air cooling hit a wall? A point where it just physically can't keep up with the latest hardware?
Absolutely. As hardware gets faster and racks get denser, especially once you start talking about racks pulling over, say, 20 kilowatts of power, air cooling hits a hard limit. It just can't remove heat fast enough for today's high-density gear. This forces performance, throttling your expensive chips slow themselves down to avoid frying. Or worse, you get system outages. And trying to fix it by adding more big AC units, that gets incredibly expensive. Or sometimes it's just not feasible because the power grid can't support it.
Which naturally leads us to what looks like the future for enterprise data centers, for the white space. Liquid cooling.
Exactly. Liquid cooling. It's pretty much what it sounds like, using fluids to pull heat directly away from the hot components. Wow. And the advantages over air, they're significant. First off, that massive improvement in cooling efficiency we talked about. Liquids are just so much better at heat transfer. This means your hardware lasts longer, performs better, and you get more uptime, which is critical.
And better efficiency usually means better for the environment too, right?
It certainly helps. Liquid systems need less energy to move the coolant around. This improves something called power usage effectiveness, PUE.
PUE, right. Heard that term.
Yeah, PUE basically measures how much power goes to your IT gear versus how much is spent on cooling and other overhead. A lower PUE is better. It means more energy is doing useful work, computing. That's great for your budget and your green credentials.
I bet it also changes how you use space in the data center. Floor space is always tight.
Oh, it's a huge space saver. Liquid cooling lets you pack way more compute power into a smaller area, supports those really dense server setups. Plus, you don't need as many huge air handlers or bulky ductwork. That frees up valuable white space for more racks, more IT equipment, and this feeds into lower long-term operating costs too. Fewer big mechanical parts like fans and AC units means less wear and tear, less maintenance. Better cooling also means less hardware failure from heat stress, fewer replacements. And here's a cool bonus sometimes. The heat captured by the liquid can actually be reused.
Reused.
Yeah, like for heating office spaces in the same building or even nearby buildings. That adds to cost savings and boosts sustainability. It turns waste heat into something useful.
That's pretty smart. Okay, so we see the general benefits. What are the main types of liquid cooling we'd actually find in an enterprise data center today?
Generally, you see three main approaches. First is direct-to-chip, or DTC. That's where liquid flows right over the hottest parts, like the CPU or GPU. Second is immersion cooling. This is where you literally submerge the entire server or component in a special non-conductive fluid. And third, you have coolant circulation systems. A common example is the rear door heat exchanger, where liquid circulates through the back door of the rack itself. Each has its own strengths and weaknesses.
Okay, let's start with immersion cooling. That sounds pretty radical, like dunking your servers in a bath. How does that work?
It does sound wild, but it's very effective. The servers are completely submerged in a dielectric fluid. Crucially, it doesn't conduct electricity. There are two main flavors. Single-phase immersion is like a continuous loop. The fluid flows out of the tank, it's cooled by a heat exchanger, and flows back in. Kind of like a constant cool bath, yeah.
And two-phase sounds more complex.
It is a bit. In two-phase immersion, the heat from the chips actually causes the special fluid to boil at a relatively low temperature. It turns into vapor. This vapor rises, hits a condenser coil at the top of the sealed tank, cools down, turns back into liquid, and drips back into the bath. The heat is carried away by the coolant flowing through that condenser coil. It uses the phase change for really efficient heat transfer.
Wow. So what are the biggest upsides to taking the plunge with immersion cooling in a big data center?
Well, performance-wise, immersion offers the absolute best cooling. It allows for the highest rack densities, some say up to 10 times what air cooling can handle. It also gives you the best energy efficiency, potentially cutting cooling power usage by up to 50%. And it's much quieter, obviously. No roaring fans inside the tank. Some analyses also suggest that heat reuse potential can lead to a better ROI, a better return on investment over the long haul.
Okay, super powerful.
Yeah.
But you know how we are on the white space? We need the downsides too. What are the catches with immersion?
Definitely some things to consider. First, the fluid itself isn't cheap. Some common ones can cost like 38 tank a gallon. That adds up fast when you're filling large tanks. Second, maintenance. Yeah, pulling a server out of a tank of fluid can be messy. Some technicians call it a big stinking mess, though newer synthetic fluids are better, less smelly, easier to clean up. Still, cleaning sticky fluid off components isn't fun. You might literally need towels.
And I heard something about standards for these fluids or lack thereof.
That's a valid point. There aren't really universal agreed-upon standards for immersion fluids yet. That's a bit of a worry, because you need fluids that are totally inert, meaning they won't degrade insulation over time or dissolve to glue on labels or react with inks on the circuit boards. Compatibility is key. Then there's the leak potential. Modern systems are well-engineered, so maybe the fear is a bit much, but any liquid leak in a data center can be catastrophic if it hits other gear. And disposing of the fluid at its end of life adds cost and environmental considerations.
That brings up complexity. What about the staff and the physical space?
Good question. Immersion often requires specialized training for the data center staff. You might even need lifting equipment, like small cranes, to get servers in and out of deep tanks. That means planning for overhead space, thinking in 3D in the data hall. The tanks themselves, or the racks designed for immersion, are often wider and deeper than standard racks, so you might need to reconfigure the room layout. And a big one. Not all standard IT hardware is designed or warranted for immersion, so it can limit your hardware choices, reduce that agility we talked about with air cooling. Finally, while it's super efficient overall, the actual operating temperature of the components might sometimes be slightly higher than with direct chip using cold plates, though it's fantastic at eliminating hot spots and cooling things like memory and power supplies uniformly.
Interesting trade-offs.
Right.
Okay, let's shift to direct-to-chip DTC cooling. How's this different? More targeted?
Exactly. DTC is more focused. You attach a cold plate directly to the hottest components, usually the CPU and the GPU. Coolant flows through this cold plate, absorbing heat right at the source. In single-phase DTC, you have a CDU, a coolant distribution unit that pumps the fluid through the cold plates in a closed loop. The warm fluid then goes off to a heat exchanger somewhere else to get cooled down again. And yes, like immersion, there's also two-phase DTC. The coolant boils right inside the cold plate as it picks up intense heat, using that phase change for extra cooling power.
So, more pinpointed than dunking the whole thing. What are the pros of this approach for data centers?
DTC strikes a really good balance. You get excellent cooling performance, much better than air, but typically with a lower upfront cost and easier serviceability compared to full immersion. Efficiency-wise, it can be, 50 to maybe even 1,000 times more effective than air cooling right at the chip. This lets those high-power CPUs and GPUs run much hotter and faster. It can typically remove maybe 70–75% of the total heat generated by the rack's components. The catch is you usually still need some air cooling for the rest of the stuff in the rack, like memory, power supplies, network cards.
And the cons for DTC?
Well, the absolute peak cooling performance isn't quite as high as you can get with full immersion, and the risk of leaks, while managed, is always there. A leak directly onto a motherboard could cause corrosion or short circuits. That's a major concern. And again, the two-phase DTC systems are generally seen as more complex to design, manage, and maintain than the single-phase versions.
Got it. Okay, let's cover the third main type. Rear door heat exchangers. These sound a bit closer to traditional setups, maybe? How do they fit in?
They do integrate quite neatly. Essentially, you replace the standard back door of a server rack with a special door that contains a heat exchanger, like a car radiator. Hot air blown out the back of the servers passes through coils, filled with chilled liquid, usually water or a water glycol mix. The heat transfers from the air to the liquid right there at the rack door. There are two main types here, too. Passive ones rely just on the server's own fans to push the hot air through the coils. Active ones have additional fans built into the door itself to help pull more air through. This lets them handle even higher heat loads, higher densities.
Okay, so it catches the heat on the way out. What makes these rear door units attractive for enterprise data centers?
Well, it's a pretty mature technology now, quite well understood. It's a very solid solution for racks generating more than that 20 kilowatt threshold we mentioned. A huge plus is that it negates heat at the source. It cools the air before it mixes back into the room. This reduces or even eliminates the need for complex hot aisle, cold aisle containment setups. It also means you can often use warmer water in the cooling loop compared to other systems. This makes your external heat rejection, like chillers or cooling towers, much more efficient. It can even enable free cooling for more of the year.
Free cooling, you mean like not needing chillers?
Exactly. Using ambient air temperature to cool the water loop, potentially cutting chiller energy use by over 90% in some climates and setups. That's a massive energy saving. They're also very retrofittable. You can often add them onto existing standard server racks, OEM racks, and they can sometimes tie into the return water loop from your existing chilled water system. Being closed-loop liquid systems, they also offer huge water savings compared to evaporative cooling towers that vent water vapor. And finally, real estate. By handling the heat at the rack, you might not need as many large Sierra units, computer room air conditioners taking up floor space. That can free up maybe 60% of that cooling footprint for more IT gear. It maximizes your white space.
Okay, really interesting options there. So we've dug into the specific technologies, but stepping back, what are the bigger picture things enterprise data centers need to weigh up when choosing their cooling path? Sustainability and regulation seem like a huge one now.
Oh, absolutely critical. There's a massive global push towards refrigerants, the cooling fluids used in chillers, and some AC systems that have a low global warming potential, or GWP. GWP just measures how much warming a gas causes compared to carbon dioxide, CO2, which has a GWP of 1. Some older refrigerants have GWPs in the thousands.
Thousands, wow.
Yeah, thousands of times worse than CO2 for the climate. So international agreements like the Montreal Protocol, and especially its Kigali Amendment, are mandating a phase down of these high GWP substances, mainly HFCs, hydrofluorocarbons. The goal is like an 85% reduction globally by the mid-2040s.
And these aren't just suggestions, they become law, right? Region by region.
Exactly. In Europe, you've got the F-gas regulation, which was just updated again in 2024. It's very strict. phasing out HFCs almost entirely by 2050, with tight GWP limits kicking in for new equipment really soon, like 2027 for many types of chillers. In the US, there's the AA Act. It gives the EPA authority to phase down HFCs, and similar rules are coming into effect, requiring low GWP refrigerants in new data center cooling gear by 2027 as well. Operators have to plan for this to stay compliant, and these newer refrigerants, they get classified by toxicity and flammability. We're seeing a shift towards A1 refrigerants, low toxicity, non-flammable, or A2L refrigerants.
A2L.
Yeah, A2L is a newer classification for mildly flammable. They're much safer than older flammable options, but require specific handling and safety measures. Data centers are generally avoiding the highly flammable stuff like propane that you might see in a domestic fridge, and there isn't one single perfect low GWP refrigerant that works everywhere. What's acceptable or preferred can vary by region due to these regulations. It's complex.
And water usage remains a big sustainability factor, too. Liquid cooling helps there.
Generally, yes. Closed-loop liquid cooling systems inherently use far less water than air cooling systems that rely heavily on evaporative cooling towers, which release water into the atmosphere. That's a major plus, especially in water-stressed areas.
Okay, regulations aside, there's always the bottom line: cost and implementation. Liquid cooling sounds great for operating costs, but getting started seems expensive.
That's often the trade-off. Liquid cooling usually has lower operating expenses, less energy, potentially less maintenance on some parts. But the initial capital expense, the CapEx, can be higher. You might need specialized racks, the CDUs, the piping. It's a bigger upfront investment per rack compared to just adding another air handler.
And what about maintaining it all and flexibility?
Yeah, maintenance is a key difference. Especially with immersion, it can be more complex, potentially more costly if things go wrong. It might slow down how quickly you can swap out servers or deploy new hardware. Air cooling definitely offers more agility in that sense. Just roll in a new rack, plug it in. Liquid cooling often requires more planning, potentially new skills for the technicians, or relying on specialized vendor support.
Location, location, location. That matters too, right? Does climate dictate the choice?
Hugely. Geography and climate play a massive role. Trying to air cool a data center in, say, Las Vegas in the summer, that takes an immense amount of energy. On the flip side, a place like Alaska might seem perfect for free air cooling. But even there, if you have racks hitting 50 kilowatts or 100 kilowatt densities, air might still struggle. So liquid cooling could still be the better option, even in a cold climate, depending on the workload.
And thinking long-term. Future-proofing, scalability. This seems like liquid cooling's home turf.
Absolutely. That's arguably its biggest strategic advantage. Liquid cooling is just inherently better equipped to handle the future. As rack densities keep climbing, pushing past 30 kilowatts or 50 kilowatts, even higher for AI clusters, liquid cooling can scale to meet that demand. Air cooling often can't without massive infrastructure upgrades. Liquid helps avoid straining the power grid, prevents those performance throttling issues or outages when you push hardware to its limits. It's about building a data center that can handle tomorrow's workloads, not just today's.
Okay, let's quickly touch on a couple of supporting actors in these cooling dramas. First, glycol. We hear that word a lot with liquid cooling. What is it exactly?
Right. Glycol is pretty essential in many systems. It's a type of chemical compound, and alcohol, actually. It's mixed with water in cooling loops, primarily for two reasons. It improves heat transfer properties, and crucially, it lowers the freezing point of the water.
Like antifreeze in a car.
Exactly like that. Prevents pipes bursting in cold weather or if chillers run very cold. There are two main types you hear about. Ethylene glycol, which is a better heat conductor but is toxic, and propylene glycol, less efficient thermally, but non-toxic, much safer for people and the environment. But now there are advanced formulas too, like one called CoolFlow DTX. It's designed to give you the high thermal performance closer to ethylene glycol, but with the safety profile of propylene glycol. Best of both worlds, kind of. So it makes the coolant work better and safer. What are the main benefits glycol brings?
Better heat transfer, that freeze protection, which is vital. And importantly, these mixtures contain corrosion inhibitors. They protect the pipes, the pumps, the cold plates from rusting or degrading over time. Extends the life of the whole system. It just adds resilience and flexibility. Of course, you still need careful handling, especially with ethylene glycol, proper disposal, and regular maintenance, checking the mixture concentration, the pH, making sure the inhibitors are still effective.
Makes sense. And the other big piece of equipment we often see are those huge cooling towers. What's their role in this whole white space cooling picture?
Cooling towers are very common, especially with larger data centers using chilled water systems. They are a type of evaporative cooling tech. Their job is to reject the waste heat collected from the data center into the atmosphere. They cool down the water that's been circulating and picking up heat from the IT equipment, usually via chillers or other heat exchangers. They're very energy efficient at doing this indirect cooling job.
How do they actually get rid of all that heat?
It's pretty clever. Hot water coming back from the data center gets pumped up to the tower. It's then sprayed down over a material called fill. Looks a bit like honeycomb plastic sheets. At the same time, large fans draw ambient air up through this falling water. As the air passes the water, some water evaporates. That evaporation process pulls a lot of heat out of the remaining water, cooling it down significantly. That now cooled water collects at the bottom and gets pumped back to the facility to pick up more heat. It's a continuous cycle.
So they're really key for the overall efficiency, the PUE we talked about.
Absolutely. By providing very efficient heat rejection, cooling towers help lower the overall energy consumption of the cooling system, which improves the data center's PUE. The energy savings can be substantial, sometimes paying back the tower's cost in just a couple years for big facilities. And it's worth noting, while you see water vapor coming off them, when you look at the total water footprint, including the water used to generate the electricity saved, efficient cooling towers can actually reduce the overall water consumption compared to less efficient cooling methods.
Fascinating. Okay, we have covered a lot of ground here, a real deep dive into cooling the white space. Wrapping it all up, is there one single best answer for every data center out there?
No, definitely not. I think that's the clearest takeaway. There is no one-size-fits-all cooling solution. The right choice really depends entirely on the specific data center, its existing infrastructure, the kinds of workloads it runs, its budget, its climate, its plans for the future. A facility with very dynamic, changing workloads might value the flexibility of air cooling more, even if it costs more to run. But for a massive, stable AI training cluster, liquid cooling is probably becoming unavoidable.
But the trend, the direction of travel, seems clear. As we often discuss on the white space, it really feels like liquid cooling isn't some far-off niche anymore.
That's absolutely the crucial point. With the way compute power is increasing, especially driven by AI, machine learning, all these advanced workloads, liquid cooling is moving rapidly from niche to mainstream. It has to. Its ability to handle heat is just so vastly superior to air. It's going to be increasingly necessary to support these incredibly power-hungry applications, whether that's in huge core data centers or even smaller deployments out at the edge, which leads to the importance of partnerships. Data centers really need to work with infrastructure partners who understand this whole landscape deeply. Partners who offer a range of solutions, air, liquid, hybrid, and have real expertise in thermal management. They can help navigate those complex regulations, choose the right refrigerants, design and implement safe, efficient systems, whether it's full immersion, DDC, rear doors, or some combination.
That makes total sense. So, thinking ahead, as data centers keep pushing the limits, maybe the question isn't just how do we keep things cool, but how can we actually use that heat smartly? Turn it into an asset for a future that's more sustainable and more powerful. What are the next big innovations you think we might see bubbling up for the white space? How might they totally change the game for efficiency? Lots to think about there. And that is all the time we have for this deep dive from the White Space Piso Blanco podcast. We really hope you picked up some valuable insights today. A final massive thank you again to our wonderful sponsors, Series Tech and Moxtel. Don't forget, all the info links are
Welcome to
next
the
time
White
on the Deep
Space,
Dive
a
for another
podcast where we
exploration
talk
into
about
knowledge.
data centers in a
Stay
simple
well.
and practical way.